Let's be honest with ourselves. For way too long, we've all been working under this convenient, but frankly kind of insane narrative that all the sciences are these separate little kingdoms. That biology is this soft, squishy, almost mystical art form, while physics, well, that's for building bridges and rockets. Today, we're going to absolutely shatter that illusion. We are going to show you with hard, quantitative evidence that your body isn't some exception to the laws of physics, it is their most sophisticated and ruthless application.
Oh, I love this quote because it perfectly captures the intellectual smackdown we're about to deliver. If you've ever had this feeling that life operates on some kind of special, unquantifiable magic, I'm here to tell you that the universe and your own body profoundly disagrees. The real magic isn't in violating the rules, it's in mastering them to a degree that is almost unbelievable. So buckle up, let's get corrected.
So, what's at the core of this whole deception? It's a simple idea we're all fed in school, to make things easier to digest, that physics, chemistry, and biology are truly distinct fields. It's a teaching shortcut that has, unfortunately, become a huge mental roadblock for most people. The reality? It's one continuous, unbroken ladder of complexity, and we're about to climb right down it.
Now, what's so great about this slide is just how brutally simple it is. Medicine, it's just applied human biology. You're not treating some mystical life force, you are repairing a very specific biological system. Okay, so what is that biological system? Well, it's just an impossibly complex dance of self-organizing chemical reactions. And what governs every single one of those reactions? Every bond, every single interaction? The fundamental laws of physics. And how do we describe those laws with perfect, undeniable precision? Mathematics. It is a direct, unbroken chain from a differential equation all the way to a drug prescription. It really is all one system.
And this just brilliantly illustrates the point. Really think about that for a second. The iron atom in the hemoglobin carrying oxygen to your cells, the very atom keeping you alive right this moment, is the exact same particle as an iron atom in a rusty nail or a skyscraper. Same number of protons, same electron shells, same quantum properties. Nature doesn't have a special bio-aisle at the atomic supermarket. It uses the exact same universal toolkit for everything. The only difference is the unbelievable complexity of the molecular furniture it's been arranged into. Life isn't made of special stuff, it's just a special arrangement of the same old stuff.
All right, so if the building blocks are universal, it stands to reason that the tools we use to inspect them should be too, right? And this, right here, is where the argument becomes really, truly undeniable. We're about to look at the so-called medical technology that doctors use every single day and reveal it for what it truly is. Industrial quality control equipment, just repurposed for meat instead of metal.
Let's start with ultrasound. We've all seen those grainy, kind of miraculous images of a fetus. It works by sending high-frequency sound waves that bounce off internal structures. It's basically medical sonar. Well, guess what? An aerospace engineer uses the exact same pulse echo sonar principle to find microscopic, hidden cracks inside a jet engine turbine blade or the wing of a Boeing 747. The physics is identical. The goal is identical, non-destructive internal inspection. The machine is completely indifferent to whether it's looking at a baby's kidney or a flaw in a high-pressure gas pipeline. It just doesn't care.
And it gets even better with CT scans. In medicine, we use a whole series of X-rays to build a detailed 3D model of your insides. It's incredible for finding tumors or analyzing complex fractures. In industry, they put engine blocks, complex metal castings, and welded pipes into industrial CT scanners to do the exact same thing. Build a 3D model to find hidden internal defects, like porosity or tiny voids that could cause a catastrophic failure. A CT scan of a human chest to find a nodule is physically the same process as a CT scan of a cast aluminum part to check for air bubbles. You're not a patient, you're a complex component under inspection.
Okay, this one has to be my favorite. A complete blood count, a CBC, is one of the most common medical tests on the entire planet. How does it work? Well, a machine suspends your blood cells in a fluid and then zaps them with a laser. By analyzing how that light scatters, it can count and size millions of cells in just minutes. So what does a quality control engineer in an advanced manufacturing plant do? They use the exact same laser scattering technique to measure the particle size distribution of metal powders for 3D printing, or the colloids in a batch of paint. The machine is just measuring a physical interaction, light hitting a small object. It could not care less if that object is your white blood cell or a tiny grain of titanium.
Let's just lay it all out here, plain and simple. Pulse echo sonar for your organs or for a weld. X-ray reconstruction for a tumor or for a metal casting. And just look at that last one. nuclear magnetic resonance. You know it as an MRI, this miraculous tool for imaging the brain and soft tissues. A chemist knows it as NMR spectroscopy, a cornerstone technique used in quality control to verify the purity of pharmaceutical ingredients or to figure out the molecular structure of a new plastic. The only difference is that the hardware is optimized for a different target. The underlying quantum physics is absolute and totally universal.
Okay, so the tools are the same, fine. But the argument goes way deeper than that. It's not just about how we look at the body. It's about how the body itself actually works. If you strip away all the biological jargon, what you find underneath are the pure, unadulterated principles of mechanical engineering, fluid dynamics, and control theory. Your body is a beautifully engineered system.
Take your own skeleton, for instance. You think of movement as this fluid, organic thing, but at its core, it's just a system of levers, pulleys, and pivot points, exactly like what you learn in an introductory physics class. When you nod your head, that's a classic first-class lever. With your spine as the fulcrum, it's designed for balance. When you stand up on your tiptoes, that's a second-class lever, a power lever, just like a wheelbarrow, that lets your calf muscle lift your entire body weight. And most of your movements, like a bicep curl, are third-class levers, speed levers, which prioritize range of motion over raw force. You aren't just moving, you are actuating a biomechanical system governed by good old Newtonian physics.
All right, let's talk about one of biology's proudest concepts, homeostasis. This is presented as the magical ability of your body to maintain a stable internal environment, keeping your temperature, your blood pressure, your blood sugar all within this incredibly narrow, life-sustaining range, no matter what's happening outside. It's often presented as this unique, almost magical property of life. But is it really?
Any engineer would look at homeostasis and just yawn, because what they see is a classic closed-loop feedback system. They'd call it a PID controller, short for proportional integral derivative. It's a cornerstone of industrial automation, used everywhere to keep a variable at a set point, like maintaining the temperature in a chemical reactor. It has sensors to measure the current state and actuators to correct any deviation from the goal. Your body does the exact same thing. Your nervous system senses a drop in blood pressure, so it acts by increasing your heart rate and constricting your blood vessels. It's not magic. It's just a robust, highly optimized control system that has been field-tested for millions and millions of years.
So, the body operates like a machine, but the analogy goes even deeper, down to a layer that's almost always invisible to the patient, and honestly, even to many doctors. The rigorous mathematical and statistical framework that underpins everything from your lab results to your prescription dosage. The numbers are there. They're just hidden in plain sight.
So you get a blood test back, right? You always see a normal range. Where does that come from? It's not arbitrary. It's a statistically defined reference range, typically designed to contain about 95% of the healthy population. Now look at the engineering column. In aerospace, to make sure a plane wing won't fail, they don't design to the average strength of a material. No way. They use what's called an A basis allowable, a statistically calculated minimum strength that guarantees 99% reliability with 95% confidence. The mathematical methods used to calculate your normal blood sugar range and the safe stress limit for an airplane wing are functionally identical. They are both advanced statistical tools called tolerance intervals designed to manage risk and variability in a very complex system.
And this right here gets to the absolute heart of the illusion. When a doctor tells you to take 500 milligrams twice a day, it feels simple. There's no visible calculus, no differential equations scrawled on the prescription pad. And that simplicity creates this powerful but totally false idea that the practice of medicine is somehow separate from the hard, quantitative sciences. But the complexity isn't gone. It's just been pre-solved for you.
So let's break down where that simple dose actually comes from. There's a whole field called pharmacokinetics, which is pure mathematical modeling. It uses calculus and differential equations to describe how a drug's concentration in your blood changes over time, how it's absorbed, distributed, and eventually eliminated. Years of research and clinical trials go into solving these complex models to find the one dose that stays in the therapeutic window for the longest time for the most people. That final 500 milligram prescription, that is the pre-calculated standardized output of all that hidden math. The doctor at the bedside is simply applying the engineered result using basic algebra. The really intense quantitative work has already been done and packaged up for simplicity.
So we've established the body is a machine, built from universal parts, inspected with industrial tools, and maintained with the same math. This forces us to ask a really powerful question. What does that make nature itself?
Well, it requires us to reframe evolution not as some random, meandering process, but as the most ruthless, efficient, and unbelievably patient optimization engineer in the entire universe.
This comparison here, this challenges our last little bastion of biological specialness, the idea of microscopic complexity. We think of cells as being unimaginably tiny. A typical human cell is maybe, 30 micrometers across? But the high-strength superalloys used in jet engine turbine blades get their incredible strength from precisely engineered structures inside the metal, called nanoprecipitates. These structures are often just 20 to 50 nanometers in size. That is literally 1,000 times smaller than a typical cell. Human engineering is already manipulating matter at a scale far, far finer and more controlled than many of the basic units of life.
And here it is, the ultimate takeaway. Life doesn't get a pass on the laws of physics. It doesn't get to cheat thermodynamics or ignore quantum mechanics. Instead, life represents the most stunning, mind-bogglingly complex, and optimized application of those laws. Billions of years of trial and error, the ultimate R&D process, have produced a machine that can self-replicate, self-repair, and even contemplate its own existence, all while perfectly obeying every single physical constraint the universe throws at it.
Which leaves us with one final question to think about. The next time you go to the doctor, are you really going for a medical consultation rooted in some abstract art of healing? Or are you taking a highly complex piece of organic machinery into a service center for a system diagnostic, run by a highly trained technician who uses the principles of physics and mathematics to get your system back to its optimal operating parameters? The evidence, I think, is overwhelmingly clear. The science is one unified, beautiful, and quantitative whole.